All right, let's talk about a titration calculation involving a strong base. We've got 0.100 molar sodium hydroxide, and we're titrating that into 20 milliliters of 0.100 molar acetic acid. We're also given the Ka of the acetic acid. So we already saw an example of the strong acid and strong base. This is a weak acid with a strong base. If we were doing the reverse, a strong acid with a weak base, we'd do something similar. So again, let's say, first thing I want to do is look at what's the equivalence point of this thing, and I don't have my other questions, but we'll just talk about a couple different volume additions to see how we could figure out the pH. So again, we've got our equation, the molarity of the acid, or the H plus if it's polyprotic, times the volume of the acid is going to equal the molarity of the base times the volume of the base. And so again, we're looking for the stoichiometric proportions of how much acid can be neutralized by how much base. So if I have 0.100 molar for the acid times 20 milliliters, and that is equal to the base is 0.100 molar, and we're looking for the volume of the base. Well, obviously if the same concentration, volume of the base, if we solve that's going to end up being 20 milliliters. So this would be my, again, that's called the equivalence point, the volume that I would need in order to have these stoichiometrically equal amounts of hydroxide to cancel out with the, or to react with the acid. And so again, in this case, for the equivalence point, it doesn't matter if it's a strong or weak acid or base. That's going to be found the same exact way. Okay, so now if I look at, so let's say I add 15 milliliters of sodium hydroxide, and again, this is that 0.100 molar hydroxide we said we're titrating with. I want to find the current pH. So this is like if you were looking at your titration plot of volume of sodium hydroxide added versus your pH of your weak acid that we did in lab. It's the same kind of idea. If I want to figure out at any point in time with any given added volume, what would the pH be? So what I'm going to do is figure out the, again, my volume is going to be 0.015 liters, and the number of moles, that is 0.0015 moles of sodium hydroxide. And again, my number of moles of the acid, so the H plus, or sorry, the HC2H3O2, since we have 20 milliliters of that, that's 0.020 liters times 0.100, oops, 0.100, and that equals 0.0020, and that's going to be moles of our acetic acid. So we have our starting amounts of what was added into this flask together. And so again, looking at the stoichiometry, so I have this much sodium hydroxide and this much acid. So again, the limiting reactant here, well, the sodium hydroxide is all going to be reacted at this point. So for my acid, I'm starting out with 0.00200 moles, and I'm reacting with that 0.00150 moles of the base, and that gives me 0.00050 moles. Right, moles of acetic acid remaining. Now the other thing here that we have to pay attention to, if this is a weak acid, when we're trying to find the pH, we need to keep in mind that there is this reacted with the hydroxide, and so we have water formed, and now we have this conjugate base also present, which is going to affect the pH. So the fact that this is a weak acid, we do need to factor in how much of the acid is left over and how much of the conjugate base is now present. So my initial conjugate base concentration we can find from looking at the equilibrium, which again, it's going to be pretty small. If I've got, in my original weak acid, we know that it's going to ionize partially into H plus and acetate, and so that's a pretty low concentration to begin with. So we'll say that's approximately 0 for start, but when we form, again, if we're reacting, this was the amount of base that we reacted, the amount of hydroxide we reacted, then this is the amount of this conjugate base that we're left over with. Okay, so again, we need to factor in the total volume that's there. So I had 15 milliliters added to the 20 milliliters, so that is 35 milliliters or 0.035 liters. And so my concentration of my acid now is 0.0143 molar, and my base, or my conjugate base, again, we're all in the same volume solution, and so this divided by the volume that's there, so this again is the moles of acetate formed, I have 0.0429 molar. And so what I'm going to do is plug into, so you can use the Henderson-Hasselbalch equation, you could use the Ka equation, so again Ka equals H plus times the C2H3O2 minus over the acid concentration, or again you could do pH equals pKa plus the log of, and then this would be the C2H3O2 over the HC2H3O2. So you could do either of these to do your work from here. So I'm going to use the Henderson-Hasselbalch just because it's all rearranged and solved for me. And so I'm going to do the 1.8 times 10 to the fifth, which is the Ka that I was given. And so that gives me a pK of 4.74, and then the log of the numbers that we just figured out. So this is the acid, 0.0143, and the base, 0.0429. And so that is going to give me 0.0429 divided by 0.043, log it, and that's plus 4.74. So I end up with 5.22 as my pH. And again, that makes sense because we're adding base, so we should see the pH climbing steadily. You notice this, again, we got this from when we were talking about buffers, but you know, this relationship just comes from rearranging the Ka, and if I'm asked for pH at any given point in time, I can solve in here or in here, but I have to figure out what are my current concentrations of my species. And because this is an equilibrium system with a weak acid, you know, we have to factor in well, the equilibrium in the Ka, and we didn't have to do that for the case of a strong acid. The other thing I want to point out while we're here is, again, if we're looking at on the titration curve and figuring out the pKa from the titration curve, which you'll be asked to do in your lab, the idea is that when we get to, again, when this ratio of the anion divided by the weak acid, when those values are equivalent, and therefore this log term drops out and becomes 0, that's when our pH in our titration is going to equal the pKa value. And so, again, mathematically you can see that that's how and why we can use the curve in that way, the titrant volume compared to the pH curve. We can use that to figure out the pKa and the Ka for an unknown acid during the titration. But anyway, this is what you would do. So we need to factor in the fact this is an equilibrium system, and that's how this is different from dealing with the strong acid and strong base scenario.